So, good morning, everyone. Thank you so much for coming. My name is Tom Zimmerman. I'm a researcher in the RISE group at MSR, and it's my pleasure to introduce Andreas Zeller, who's a full professor at Saarland University in Germany. And he was actually my PhD advisor, so I'm really looking forward to the talk. Andreas is one of the top people in software engineering research. He is an ACM fellow. He won several most influential paper awards for his work on mining software repositories and automated debugging. And in more recent years, he has done much more work on security, and we're looking forward to your talk.
Thank you, Tom. Thank you very much. I was making jokes because I became ACM fellow for our work on mining software repositories, among others. Okay, so I guess that's great. It's always nice to come back to the Seattle area. I just noted that it's now 18 years ago since I came here the first time, and it's amazing how much things have changed since then. So I was strolling through the city yesterday, and I found that the Alaskan Highway is now ripe for demolition, which people were talking about 18 years ago. It's nice to see the new 520 bridge now in operation, which people were talking about 18 years ago, and I understand that in only 7 years there will be an extension to Microsoft. I see. So before I retire, I will see all the beautiful things that people have been talking about all these years.
You must plan to work for a long time.
The place where I come from. So this is Germany over here, and this little pixel. 2 times 2 pixel thing here. There's the state of Saarland, and this is the city of Saarbrücken. Well, I also arrived there 16 years ago, and we've had no new bridges or no new. Well, we got a new light rail, yes, but it has 2 new stations too, very much like the one over here. But the place actually, but things don't change that much. It's fine, and it's good because things are good as they are. Although there's one particular point where things do change, and if you haven't been to Saarbrücken for some time, this is our newest building in computer science. This is our, I think it should be our 10th building or so that we're getting there. This is an all-new center for IT security, and earlier this year it has been announced that this center is going to be expanded massively. Right now there's about 100 researchers in there. It's going to expand to 500 researchers in the course of the next 10 years. So meaning that right now we're having one application talk every week, and is going to remain that way for the next 10 years, which is fun. So if you have any friend who for some reason doesn't like to go to Microsoft Research, which is also what I recommend to my students, and who likes to work in security, ask them to check us out. It's a very dynamic place to be in. And what I'm doing there is, among others, the work that I'm presenting today. This is mining input grammars for security testing. Although this is this is not the best title for this talk, as I realized, unfortunately, only yesterday, because a much better title for this talk would be something like making $50,000 a month by fuzzing software. And now that I have your attention, see, money is a great motivator. And let me tell you how we're doing this. So, fuzzing is what most of you know, I very much suppose, is the idea of feeding programs with random input at the system level. This is Bart Miller, who invented the term and the technique in 1989, and the paper today is a classic, an empirical study on the reliability of Unix utilities, where Barton and his students went along and created random inputs, fed them into the Unix utilities at the time, and saw them crashing and hanging. And actually a very wide number, 25 to 33% of them, because they were never ever subject to such inputs before, actually crashed and hanged. This is a typical output of a fuzzer. It's very easy to build a fuzzer. Actually, that's 5 lines of Python code, which will happily produce inputs like these. I'm sure there is a programming language where this is actually a valid program.
It's called Java.
Yeah, not exactly sure. Maybe we can feed this into a Perl interpreter of sorts or something else. But the thing is, there will be lines in there which simply are very long, so programs are prone to buffer overflows. Anything that parses things will check, say, for strings, for beginning of a string, end of a string. So there's many ways that programs can fail simply by scanning this input. And at the time, yes, plenty of different utilities on the various Unix flavors of the time, on Sun, on Solaris, on IBM, and so on, all happily failed. Actually, the nice exception to the rule was the GNU tools, which already existed at the time. They turned out to be the most robust ones, and this is also the base for the tools we're having today on Linux. And since then, of course, 1989 has been a long time. Anyone now knows how to fuzz a program. The reliability has much improved. And today it's actually pretty hard to get any of these systems to crash if you use the same technique as Bart Miller did in 1989. But the thing is that parsers that we have today, that are written today, are much more robust than the parsers we had in 1989, where people only began to imagine that there could be some weird input that feeds into one's program. The problem is that a well-written parser will happily reject all invalid input as invalid, and you will never ever reach the code that actually matters to you, namely the runtime system, the deeper layers that come beyond the parser, where you would like to find bugs, or whether you'd like to find successes. However, if you do have a syntactically valid input, that is, an input that is actually processed by the parser, then you have a chance to discover bugs in those later stages that happen, that then process the input as parsed by the parser. And that's and in order to get such a syntactically valid input, there's what we need is a description of what makes a valid input. This is called the input language of a program, and we all know there's language theory for that. And what we can do is we can create a grammar that describes the input structure, the syntactic rules of the input, and using this grammar, we can then produce syntactically correct input. This is something we did, a student of mine, in 2012. Now that's 5 years ago. And my student, Christian Holler, built this whole thing for JavaScript. He built a JavaScript grammar, which actually was quite some work writing this down. And using this JavaScript grammar, which he created, his tool would then happily create inputs that are indeed valid JavaScript and feed these to JavaScript parsers, such as the one that is found in Firefox or in Chrome. And this input, as you see it over here, was one of the first inputs that actually crashed the parser, or that crashed the JavaScript interpreter, which actually is a serious thing, because if you can manage to crash an interpreter, or the JavaScript interpreter, this typically is the base for a later exploit. And if you have an exploit in the JavaScript interpreter, that's very serious, because this means that you can take over the entire browser and then collect arbitrary data from the user. Browsers today are like operating systems, so you get full control over everything. The interesting thing about the work of Christian, this fuzzer, was that it not only would it produce arbitrary random inputs, you could also use the very same parser to parse existing JavaScript programs, of which there were many. And to top it all off, he used his parser to parse existing JavaScript programs from bug reports, which were known to have caused troubles before, and he used them to parse them and then to recombine them. So in a way, he was looking at reports of, say, the measles and cholera, parsed these two, recombined them, and created new strains that would then feed all of these to the interpreter in the hope of triggering new bugs, which was lots of fun. It also was very successful. Over the course of 9 months, he got 18 Chromium Security Awards, 12 Mozilla Bug Bounty Awards from Google and Mozilla, respectively. And more specifically, he gained $50,000 in bug bounties in the first 4 weeks of running his tool. Running his tool on a single machine on a laptop, so we're not even talking about a server farm or anything. This is him, this is Christian. After these 4 weeks, so he got to the top of all the security leaderboards and everything, so that was fun. He got hired away by Mozilla at a quite nice salary. It's not $50,000 a month, but it's steady, it's fine. And his job description was simply to continue to run his tool. That was fun. And that's what, so he's running his tool for 5 years now. He's perfecting it. He's, in these 5 years, since, well, that's 1 year ago. Since one year ago, when I last asked him, his tool had found 4,000 bugs. Had found 4,000 bugs in the JavaScript interpreters of Firefox and Chrome. All of these bugs confirmed by developers, fixed, so all the shebang, all that's there. And by the way, while for Mozilla, Mozilla gave him the authorization to still run his tool on Chrome, where he still gets bug bounties once in a while as a side business. So he gets the steady income from Mozilla, and he gets the bug bounties from Chrome. So he's perfectly at ease.
So these inputs, they trigger buffer overruns?
Yes, this is buffer overruns. This is all sorts of ways to cause the interpreter to hang or to crash. So it's buffer overruns, it's bugs in the optimization stages, in the just-in-time compiler, everything. And as I said, most of the largest success comes from the fact that his tool is able to parse existing bug reports and existing inputs and recombine them. So not only are his inputs not completely random, but actually there's a stronger resemblance to existing code. That's one thing. And the second thing is that if you search in the vicinity of existing bugs, you're likely to find more bugs because as we know, bug fixes, aren't always perfect. Sometimes they treat more the symptom than the cause. And if you search in the vicinity, you're going to find more. This is what made his tool particularly successful. When a taxi driver or asks me, so what do you do for a living? Meaning that I'm a professor. Oh, so you're running from my taxpayers' money and everything. So. Have you already done something that actually, have you done something where you can pay things back? Okay, you at Microsoft get asked this all the time, but for me this is rather rare. Then I can ask this taxi driver, so which browser are you using? Oh, I'm using Firefox. And I can tell, yes, it's because of the fact that you can use Firefox and it's all safe is, well, to some extent, to quite some extent actually due to our work with my student at the time. And then he's very happy and everything is settled. So this is work that's already a couple of years ago. It was very nice. We loved it. We also had a nice Usenix paper out of it. But one thing that, so in principle, one could do this for every program. But the problem is that, well, you need a grammar in the first place. And creating such a grammar for a non-trivial input, and most inputs are non-trivial, it's actually quite some work. For Christian, it took him 3 months to create this JavaScript grammar. And if you want to have a real working grammar for C programs, for instance, just in order to do some refactoring work or things such that you have a good parser for it, that's actually something quite expensive. I think you have to shell out about $10,000 for a single license for a good C grammar, for instance. Yes?
But in some sense, you don't need a really good grammar. You just need a good enough grammar. So you could write a grammar that is much more permissive than it needs to be and rely on the real parser to throw out the invalid.
To some extent, yes. If you want to have a grammar that simply produces lots of JavaScript code, you can deal with a grammar that only deals with a subset of JavaScript, for instance. But if you want the very same grammar also to parse existing inputs and to recombine them, it really needs to go down to the tiniest details in order to be able to process all these.
You could always use the real parser to filter out.
That's right. That's right. If you're yeah. So there's two things in here. So your grammar may over approximate. That is, it may produce more inputs that actually not valid JavaScript. Then in this particular setting of fuzzing, well, you're going to live with whatever 20%, 50% of inputs that will simply be rejected. So that's all there is. You're just wasting a bit of time. But if you have a grammar that is that under approximates, you're going to miss out a couple of features which will not be tested, and then you will miss out the bugs that are in there. So that's the downside of the whole thing. So there's these two sides. But then we're talking about context-free grammars here anyway, and JavaScript has plenty of context-sensitive features as any programming language. So actually, Christian also had to do a couple of tricks in order to deal with identifiers and others, in order to have the parser accept more input. So what we started to reason about was at the time was the idea of whether it would be possible to learn such grammars given not only a set of samples. There's a couple of works that do that using machine learning, but actually using the program at hand that processes those inputs in order to learn how its inputs are structured. And the way we built it is as follows. We do have a set of inputs, which can be a very small set. Actually, we're aiming to get this set to be the empty set. We feed these inputs to a program. We observe how the program processes these inputs. We do this dynamically. We have a tool called AUTOGRAM, which observes how the program processes those inputs. And out of these observations, it produces a grammar. This grammar can then be fed into a fuzzer, which then happily will create more inputs towards the program, thus creating in the end a virtuous circle where you learn more and more about the grammar and the program itself. So how does this work? Think of a program that processes a very simple input. They say URLs. We all know what URLs are made of. And the idea is as follows. A URL is made out of different parts. We do have a protocol, we do have the host name, we do have a port, we do have a login. You should not use logins in URLs because they're transmitted in the clear, but they provide this. And there's also a path. So these are standard elements, and we do have a couple of separators in there. And all of these elements, while they're being processed by the program that processes a URL, all of these individual fragments go through different paths in the execution. So the protocol, for instance, the protocol is being used to determine what is going to be parsed, how the rest is going to be parsed. The host name is going to end up in some DNS resolver function that is going to return us an IP address to which we are going to connect using the given port. And then over that connection, we're going to send out the login as well as the page request. And all of these individual fragments go through different paths through the execution, and they end up in different functions. And this idea that there is a natural separation of concerns in the program execution that corresponds to the structure in the input is what we want to exploit. So all of these different functions, for each fragment different functions that are stored in different variables, this is the feature, this is the basic idea where we want to be able to extract the structure of the grammar. So how can we do that? Essentially, we have explored two ways, one very thorough one and one very simple one. The first technique that we looked at is to use dynamic tainting, which essentially dynamically during execution attaches a label, a tag, to individual data as elements as they're being processed, and this tag propagates along the computation. So for instance, this tag in our case labels all the inputs with their origin, that is the input source and the position in the input. So for instance, we can track where the port goes to, and even if the port gets converted to a number, the number inherits the tag of the string, and the port then carries that tag over to the function. So we can track all of these inputs down. The second technique is much simpler. This simply consists of taking a memory dump at a particular point in time and simply looking for all string variables, whether any of these string variables contain some characters that also happen to occur in the original input. This is much simpler, it's much cruder, there's also room for error in there. But it turns out that the latter one is something that one can actually implement much easier than the first one. And I had some fun a couple of weeks ago implementing the second technique in Python. In Python, tracking a variable is in Python, accessing memory during execution is a very simple exercise. You do have a function that is called setTrace, and you pass this, and you have this API called setTrace, and you pass it a function which is called traceIt. And this traceIt function is going to be called for every single line that is executed. And with every line, you get past the current frame, the current event, meaning that a new line has been executed as well as other information. And in the current frame, you can then look up all the local variables and all of their values as Python elements. It's very simple. So actually writing a debugger in Python is 12 lines of code. Okay, so compare that to Java or C, where it's no fun at all. In Python, dynamic analysis is a breeze. And what we do is we access all the local variables, we access all of their values, and then we simply check for the values if it's a string, and if it has two characters or more, and if this value also occurs in the input that we've seen, then we simply store the variable that we have, store the variable and the value that we have just seen. So we just track these. And let me show you how this works in a real code. So here's the very same code again. I do have a function which is URL parse. I do have a couple of inputs which I pass to them. And very down here, I should have precisely the function that we have just seen. So I'm using this trace function thing. Where is it again? So 1 second. Here we go. So this is the set tracing function. I am producing some output, and for every value, I'm saving it. I'm accessing the individual variables, and I'm saving those that also occur in the input. Now, if I run this on URL parse, this is precisely what I get. So I get that during URL parse, a function which I have not implemented, which I've never seen. Actually, this would be something. I've never looked into that. There's a variable called URL, which holds the path. This is one part of the input. There's a variable named fragment, which, wow, lo and behold, it's the fragment. There's a variable called scheme, which happens to be the scheme. There's a variable called netlock, which holds the host and the port, which is precisely what we have over here. And there's a path, which, very much like the URL, also holds this very path over here. And I can now go and also apply this to other inputs, just for the fun of it. Where are we? Let me make this the first input. So here I am, happily hacking along. So here's another URL. And here we also have a scheme, which now is HTTPS. And we do have a netlock, again, a location, which also occurs in here. So you can see that simply by looking at the variables, I can already extract the individual lexical items as they occur in the input. So from this, I can now go and use this knowledge that the input is decomposed into these variables to derive a grammar. Namely, in 2 steps. I start with a very simple grammar that simply says, my grammar consists of precisely this input. This is very trivial. Anybody can write a grammar like this. And then you create a disjunction over multiple inputs, and it's all very simple. That's not how you do it. Okay, well, and what we do then, yeah, sure, grammar inference can be a very easy thing. It's actually 100% sound, so it's cool. every string in that grammar is a valid input. So, and then what I do is I go and for each and every variable I see, I introduce a rule by replacing all the occurrences of that value by a non-terminal, and then I say this non-terminal expands to the appropriate value. Let's try that out with the values that we've just seen. So here's my initial grammar. Here we go. And now I apply the second rule. I go and for all of these variables, I introduce appropriate new rules. So let's start with netlock, for instance. Netlock, this is this one. So I'm going to replace this string as it occurs up here by the netlock thing. So this is what I get. So now I have this expansion to netlock, and I see what netlock is in here. I can do the same for the scheme. I can repeat the same thing for the path, for the fragment, as well as finally for this URL variable, which doesn't really belong here. I guess it's some sort of misnomer, but that's what you get. And if I do this again, then I see that the path is in fact a URL, and the URL is path. All these names are well chosen except for the URL one. I have no idea what the folks in the URL parse thought of when they gave this variable this name. But what you can see here now is how we have decomposed this grammar input into a nice little thing. So our URL starts with a scheme, followed by location, followed by a path, followed by a fragment. Now, this is just for one single input, okay? And of course, I want to extend this to multiple inputs. Yes?
Very simple tweaks could break the scheme, right? For example, if the user had capitalized all the URL names.
Yes. I'll come to that in a second. Wait a moment. We'll gradually expand this whole thing. Okay? So this is just for one single input, and this is just one decomposition, the one decomposition we've seen for that input. Now the idea is that I can go and do this for multiple inputs, and for multiple inputs, what I'm going to, I actually have implemented this whole thing, so here we go. And if we implement this and if we run this, this is precisely the grammar that we get. So this is just live here in Python. Note that this is a fully self-contained Python program, and we are at line 200 here. So it took me 4 hours to build it, to design it, to build it, and to quality control it. So that was something that was not very hard to do, and this was very annoying for my student who had spent a year building this whole thing for Java. But his work is much more sophisticated than the very crude thing I'm having over here. Now the interesting thing is that I can repeat this thing for multiple inputs, and I can easily merge these grammars together. And since I have the structure, I can merge them by rule. So for every single rule that I have, I'm simply going to add a disjunction for the next value that I see, which actually represents the individual variables, the individual values that the respective variable can take. So if I do that, and I'm going to spare you the code for that. This is not very nice code, but I'm simply going to run that. So what I have done now here is I have taken 3 inputs with different schemes, for instance, and now you see here's the disjunction. It's HTTP or HTTPS, and the fragment variable, once is ref and once is ref2, and the host, of course, can take different values, and the query, we now have a query. This is one of the inputs. Well, there's just one variable in here, so we have a path that can take the value, that has taken the values /path and /bar, and over here we see the various schemes that there are. So we see that there can be something. You can have something with a fragment. You can have something without a fragment. You can have something with a query and a fragment. So these are different expansions. And if I would add now some syntactic sugar, I could go and say that the query in here and the fragment are actually both optional. Now, if I have such a grammar, and indeed I can start with this very grammar, I can immediately use this for producing various combinations, which then gives us various combinations of the individual constituents. And then I can create arbitrary combinations of hosts and paths and references, and for some reason no query in here. Good, where's the query? Oh yeah, hasn't expanded. Let's try that again. Do we see a query? No query. How come? Good, here we go again, another combination. So every time I can use this to roll the dice, use an arbitrary expansion, writing a producer for a given grammar. Again, this is 8 lines of code, not very complicated. Okay, and of course, the more elaborated my grammar gets, the more alternatives I have, and the more possibilities for combination follow. So as I said, this is a very simple program. We use these programs for teaching. I'm having a course on security testing. The next one starts mid-October. And we are indeed showing folks how to create such grammars and how to mine such grammars. This is the very program we're giving out to students, such that they can then try out and see how it works. Now, this is just a very simple version. Okay, there's still lots and lots of pieces missing, but it's clear how you can. It's clear that there's ways to further expand this, and we now get to our real implementation, the one that my student took a year for. This is now for a real programming language, so we're working with Java. I never tried to submit a program where I'm saying, I never tried to submit a paper where I'm saying, this works beautifully on this 20 lines of Lisp or this 10 lines of Python. For some reason, it has to be this big Java program or this big C program. So I'm always fearing that if I submit something that works on Python, people won't take it seriously. So we built this whole thing for Java, and it has a full-fledged grammar inference for Java programs. This is actually the first technique ever that is able to mine input grammars from programs. What we did have before was mining such grammars from samples, which is very nice. Google has implemented quite a number of machine learning techniques that tell you that if in a PDF document you have this token and this other token, then typically this next token is going to follow. And you can create valid documents with that. The problem, though, is that this is not going to tell you, well, it's only going to give you those documents that look realistic, but it's not going to give you documents that explore all the other possibilities there are in the program. Which is why
Which paper Google does that?
Google does that, yes.
Which paper is that?
I don't know whether they have a paper, but I spoke to Domagoj Bobic at Google. I was not under NDA, and he told me that.
We have an AC paper this week, does it?
And there's work with Patrice Godefroy. Yes, machine learning for fuzzing. Yes, sure. So you have the same paper. I think they never bothered to write a paper about it. Okay. Yes, I know that work. And also there's people at Stanford. This also appeared this year at PLDI, where they have a great technique for inferring grammars using some active learning of the program. But our idea is to have the program as a reference to extract the grammar for it. Okay, not samples, nothing, as little as possible. And so our Java implementation uses dynamic tainting. So we don't look at memory dumps. We simply follow all characters. We also do some active learning to check for repetitions and optional parts. That is, for each and every grammar element, we actually go and find out what happens if we leave that out, and if this still results in a valid input. If the program under test still accepts this, we know it's optional. For every element, we try repetitions, and if it accepts multiple repetitions, we know we can repeat it. That's fun too. And very nice too, we do have a number of predefined lexical items, such as numbers and others, which we identify. So these are regular expressions. And if we find out that some input matches a regular expression, say such as a number, we try out more numbers. And if we find that more numbers are also matched, we know that this is a number. And we also have a hierarchy of these. We also have a hierarchy of these expressions. So we have natural numbers, and next coming up is negative numbers. And this is how we find out that a port number, for instance, only can be a natural number, but cannot be a negative number. I have no idea what happens if you pass a negative port number, whatever is going to happen. I remember that if you kill a negative process on Unix, if you kill a process and give it negative process ID, the entire group is going to collapse. But no idea what happens if you open a negative port. But anyway, we now know from our work that ports cannot be negative in the URL. Okay, and I'm going to give you a couple of examples of what this actually looks like. So this is again our URL example that now with our AUTOGRAM prototype applied on the Java net URL parser. And this is the grammar that pops out of it. This is the raw output of our tool. Okay, just as in the Python example that I've shown you before, we make use of actual variable names and function names in order to make this all very readable. And here you can see what is a URL. A URL starts with a spec, and there's a string in the beginning, and this string is a protocol followed by an authority as well as by an optional path. The authority consists of an optional password at a host. The host is mandatory, followed by an optional port. The protocol in our example here is always HTTP. The user info is a given, but the host is a host name. The port is a sequence of digits. The path is actually a path. The query and the references are all alphanumeric characters with special characters in there. And this is what we learn from this one single example only. So simply by looking at this one single example, which now has a couple of features, and generalizing over it, and finding out which parts are optional, finding out which parts can be repeated, we get all the generalizations that we get in this anti-grammar. Yes?
Protocol was not generalized to alphabets.
Yes.
Ref was. You do some kind of checking afterwards? Or?
So the protocol is something we cannot generalize because our tool has no knowledge about HTTP protocols. If it had knowledge about protocols, then I think it would be cheating at some point. So we cannot find, so we can generalize over individual protocols. What we can find out is that we cannot generalize protocol to an arbitrary string because arbitrary strings would not be accepted. But we cannot find out that other protocols, say like HTTPS or file or something, would be accepted. We would need extra inputs for that. The reason for that is simple. The way the Java URNet parser works is for a given protocol, if you pass that in, it's going to look whether there's any class in the class loader that matches the appropriate name. And if there is a class, it's going to load it and then it's going to execute it. And we cannot, we cannot come up with a neat and universal mechanism that at some point would search the file system for Java files that match specific file names. So that's not something we can do. So we don't know this. But the other parts, yes, the path, the query, reference, and all others, this can all be systematically expanded such that we know which parts are actually part of the grammar. You had a question? Not now?
So,
yes?
When you're doing the taint tracking, you're not looking at the path of the taint, like the control flow of the taint.
We're not looking at the control flow, we're only looking at the data flow. Thing is, if we look at the control flow, if we look at implicit information flow, that would be the correct term, then we would very quickly find out that everything depends on everything. And so we only look at the data flow. This is a limitation, for instance, so this technique works because we have because the URL parser is a handwritten parser. If we apply this technique, say, on a table-driven parser, such as a generated parser, we would not be able to find out that there is information flow along all these table elements, because all of these are governed by implicit information flow. Generally, if you have something like switch and a character, and then in case of that character do that, in case of the other character do that, you have a control dependency. And this is something we cannot we have to find, this is something where we still have to tune which kinds of control dependencies we want to look at and which others we don't want to look at. But there is a couple of expansions which goes into that direction. On the other hand, if you do have a table-driven parser, chances are that you do have a computer-readable grammar in the first place, because that's where these table-driven parsers are typically generated from. I can give you another example. This is actually a Microsoft one. This is ini files. This is a Java parser for ini files, and here you can see, so ini files, that's key value pairs with an equal sign, sections in square brackets. The essence is in here, so you have lines that consist of sections or key followed by an arbitrary number of blanks, followed by a space, followed by an optional value. The key is not optional, the value is. I didn't know that you can have something without values. And all of this is in here, and these lines then are separated by new lines, and they all are combined into one single grammar. You can see that this is a bit convoluted. So you can see here there's a first line that's first being parsed, so there's a first section, and here again we have the section down here again. That's because of the way this ini file parser is written. And I should say it's not very well written. It's looks like a crude scanner. But then these individual elements that are in the implementation are also reflected in our grammar again. But still, with a bit of manual cleanup, this becomes a very beautiful grammar. And here's my.
So you do have
Yes.
connection patterns. So in the sense, I mean, I would have expected you to generate things like it's either line 1, line 2, line 3, line 4, or line 1, line 2, line 2, line 3. So you have a way to take a sequence of lines and generalize it to a line star.
Yes, that's what we do too. Yes, this is a repetition recognition, and we can find out that we find out that the input is valid if we have no lines, if we have one line, and if we have multiple lines. And this is how we can then generalize that there is a. Is it a clean star? I think it's a clean star. So we can find out that individual elements can be repeated arbitrary number of times. Likewise here for the spaces and others. And here's my this is my all favorite. This is for JSON. So this is again one single input. So one single sample suffices. This is a constructed example where we actually look for various ways of number formatting because these make up different parts in the parser. And again, we feed this into our AUTOGRAM. And this is the grammar that comes out of it. And I'm very much in love with that grammar because it's almost textbook quality. You see, what is a JSON file? The JSON file is a value. And the value is either a string or false or true or an object, an array, a null, or a number. A string is something called a hash, which is a bad name, but I'm happy with it. Something enclosed in double quotes. False and true are, well, false and true. An object is a string, a key value pair, followed by more optional key value pairs, as many as needed, separated by commas, and with a closing parenthesis at the end. An array is similar, except that we're using square brackets here. Null is a null, a number is an integer, followed by possible fraction, an exponent. All of this is in there. And again, this is what a tool produces from one single input, okay? And there's so many things you can do with that. You can use this immediately for understanding what the input is made of. Because we know what JSON is. Okay, so we can see that this grammar is valid, but now imagine you have some unknown file format, and this is what pops out. Or you can immediately use this for fuzzing, because you can immediately create tons and tons of valid JSON inputs. You can use this to compare multiple versions of a program against each other. You take one JSON parser, take another JSON parser, you find out what the difference between the two grammars is. So it gives you plenty of insights about how the input is, about what the input looks like, and what you can do with it. You had a question?
Yeah, so the name that you're giving to the
Yes.
terminals and non-terminals, is that pulled from like identifiers within the...
All pulled from identifiers, mostly
so there's
variable
like
names.
some alpha num with white space or special white spaces?
The ones that are
or...
the ones that are underlined here, alpha num with a special white space, these are our predefined ones.
So
I just noticed that string internal is not, this is actually false. This is part of the grammar in here. But the ones that are underlined in here, this is true up here. Integer here and positive integer, these should also be underlined. These are our predefined ones. And we have a paper where this is described. These also come as part of another grammar where all of these are being defined. So we simply recognize that something matches this regular expression, and then we know that that this, for all the positive integers that we have generated, actually holds. And after a couple of, I think it's 5 trials, after 5 trials, we know, well, we've seen it work for 53, for 4,700, and for 3 more. Then we assume it's a positive integer. We could also do some Newton iteration in order to find ranges and other stuff. That's all in the works. You have a question?
I'm thinking more about learning cleaning styles. So if you look at object definition,
Yes.
What is the granularity of trying cleaning style? Does it try all possible sub-expressions in the grammar or only one?
Yes, what we do is for every element in one rule, for individual element in one rule, okay? For individual elements in one rule, we try to omit them and we check whether the input is still valid. Let me just check. I think we also do this for larger groups. So we first do this for individual elements, then for pairs, then for triples, and so on. It takes some time. So this JSON inference is a number of a couple of minutes, but well, you do it once and then you have it. So there you go. Yes.
What do you do in the absence of variable names? Let's say like someone uses capture hoops or something, and then you have arrays with
Then all of this becomes x1, x2, x3, and so on. So we cannot find these. We cannot find these out either. But even so, the simple fact that so it's not only the names that make these readable; it's also the structure that follows from it. Okay, because you can really see how this. So if you look at the JSON implementation, this structure of the grammar very nicely reflects the structure of the program that processes it, and you can obfuscate lots of names, no problem. But if you start obfuscating the structure of your program that processes inputs, plenty of programmers who will work with your code later on will be extremely angry at you. So you should come up with, if you want to really obfuscate things, you also need to come up with some mechanism. Oh, that's really bad. You need to come up with a mechanism that not only obscures the control flow, but actually that also obscures all the data flow in your program. So you would have to split these things into multiple variables. But even so, if you say, I'm going to store the first 3 characters in one variable and the next 2 characters in another variable, all that's going to show up is that there's a rule in here that says that false is composed of 2 parts, and the first is FAL and the second is SE. So, yeah, it's, so right now, there should be ways of obscuring this, but right now we're rather interested in bringing more light into what's happening here. So, these are just 3 examples of our AUTOGRAM tool. And yes, we do have a couple of exciting work that's dealing with that. So right now we are re-implementing this whole thing for C programs. And the reason for that is that we found that our technique for tagging Java elements and actually changing their representation is still something that is very brittle. So whenever we have a new subject, and in particular more larger, more complex subjects, we typically run into bugs in the Java interpreter, which in Java virtual machine. So we have many ways of getting the Java virtual machine to crash. That's very interesting, but it doesn't help us because we need to build appropriate workarounds. So now we are building this whole thing for C programs, for which we do have nice interpreters and instrumentation infrastructures that are way more solid. Plus, there's more interesting system-level utilities at the C level. Think of all the operating system parts, all the daemons, the protocols, all the data exchanges. All this is written in C, so it's fun. With this active learning, we already can do with a minimum of samples. One single sample is great, so we can explore all the variations. But in the long run, we want to do this without any samples at all. So for JSON, we have for JSON, in a Spike solution, we have managed to create a nice little test generator that is oriented towards the parsing technique that is able to systematically generate all the different variations of JSON. That was nice. And now we're generalizing this towards more programs. So which means that in the longer run, you'll be able to take an arbitrary program, feed this into our technique, and out pops the grammar. This is the long-term goal we're aiming for. The fuzzing part, interestingly, has lots and lots of open issues because you want to apply techniques you want to apply a couple of tricks on test generation. For instance, you want to fuzz in order to get a maximum of code coverage or feature coverage. You want a simple thing, covering all the production rules, okay? That's in our Python fuzzer, that's 30 minutes, 1 hour of work. And it turns out this has not been done before. But as soon as you systematically try out to come up with all sorts of various production rules, you get a much better coverage of the program. And that's because the grammars we're having here and the functions, and that's because the structure of the program is reflected in the structure of the grammars. And so if you cover the structure of the grammar, you're also going to cover the structure of the program. This is very helpful. Integration with symbolic testing. Grammars on one side, program semantics on the other side. How do you bring these two together? So what we can do, and what one of my students is working on, is to create local solutions with symbolic constraint solving at the function level, that is determining how can you reach a particular behavior in the program, so solving those constraints, and then finding out, well, this variable, which I need to have this particular value down here in that function in order to achieve that goal, is something that stems from this element in the grammar, because this is something we have established earlier with dynamic tainting. So we can find out, oh, if you pass a -1 down here, it's going to crash. We can lift that value back to the grammar and see, well, let's put a -1 in here. Maybe the -1 will be rejected by the parser, but at least that's worth a try. And in the end, what we want to build is the world's best fuzzing platform. Yeah, I'm competing with the pros here, I know that. But yes, we want to build, we want to bring all of this together, creating a platform where you throw in a program where we can infer the structure of the input, where we can apply smart test generation techniques based on the structure of the input, and then cover as many features as possible in a minimum amount of time. And fortunately, I'm not alone with that. I do have a couple of great postdocs and PhDs. We do have Rahul Gopinath from Oregon State University, student of Alex Gross, who's working with me on all the creative parts of that. Nicholas Havrikov is working on creating the fuzzer. Matthias has created the first implementation of AUTOGRAM. Alexander is working on the integration with symbolic testing, and Björn is doing all the work on C programs these days. And this is the army of folks who is helping with it. I'd like to point out that I wrote the Python program. So, yeah, for somebody who increasingly relies on others to write programs and build stuff, it's I'd like to point out that I also can write stuff myself. So just to point that out, German professors can write code too. You're happy to analyze my Python code for whatever features, but occasionally I write stuff. Okay, and in the long run, yeah, this is fun. I looked up file formats in Wikipedia. There's a page that's called file format. There's a list of file formats. These are all the file formats that are documented somewhere in Wikipedia. There is about, I think it's 1,000 different file formats, all possible 3- and 4-letter combinations. File extensions are written in their JPEG format. You don't know everything under the sun. .cr download. No idea what this is. Oh, it's Google Chrome, of course, and we wanted to be able to infer those formats one after the other, and then be able to fuzz them all. As I said, this very simple question: what is the input language of a program? This is a very simple question, and it's awfully under-researched. It's a question that's very fundamental to all sorts of testing, and of course to program understanding, at least of data understanding. But inferring this automatically is something that, at best a handful of people have undertaken in the last decade. And how can I leverage this input structure in order cover, understand, prevent particular inputs. If you have a parser for particular inputs, then you can say, okay, here's this legacy program which has a couple of vulnerabilities. I'm going to restrict its input to only those inputs that I know that are legal, or the other way around. I know that specific inputs are malicious. I'm going to infer grammar for these. I'm going to explicitly prevent them. There you go. You don't even have to patch the program for your 2-year-old IoT device, which you bought at a cheap price and which no longer is maintained. Well, at least you can set up a filter for that. All of this translates also into better understanding of code, because if you know that this part of code processes this particular input, well, you have a deeper understanding of what's going on. And of course, this also gives you an idea about how to cover specific behaviors, how to understand behaviors. There's hundreds of open issues, but it's very easy to start doing research. If I can write a Python program that infers a grammar in 4 hours, you can do so. I'm sure you folks can do so in 1 hour, including learning Python. So, so please enjoy it all. Okay, and this gets me to the end of my talk. So what have I shown? I've shown you how to use grammars for fuzzing of existing programs. The obstacle to that is getting a grammar in the first place. And I've shown you, well, both a Python prototype as well as our AUTOGRAM prototype that is able to infer such grammars automatically, and the current work of my students happily working on extending this idea in various directions. And there's plenty of research opportunities around it, and all of this can actually be found on our webpage that is devoted to AUTOGRAM. You also find our most recent technical report with all the features on active learning there. So it was my pleasure to present, and I'm happy to take questions. Thank you very much for your attention. Yes, Chris.
So really cool. I really like to talk about creative and the results. It's kind of exciting. So my question is input. So it seems like you're focusing mostly on input that is human readable, and inputs often inputs, whether it's file formats or across the wire, is binary.
Mm-hmm.
Typically, at least in my experience writing decoders for these things, they're not context free.
Yes.
You'll have like some, length encoded array or something.
Yes,
like
yes.
Do you have a sense of how well these type of approaches would work in trying to handle that, where the output is not a context-free grammar, but something else?
Yes. So there's two important issues in there. The first one is context, as you put it. What we infer here is context-free grammars, and there's plenty of plenty of data formats. There's actually in most reasonable formats, there is some amount of context sensitivity in there. You would normally not want a context-sensitive grammar to describe these. You can say, for instance, suppose you have a checksum, for instance. Okay, you do not want to describe the checksum using a context-sensitive grammar. Okay, you can do that. Okay, but that's not fun. I mean, you look at regular expressions and say, I'm not sure about that, but programmers love regular expressions, and for 100 regular expressions, you have one grammar, one context-free grammar, that is, and I'm pretty sure that for 100 context-free grammars, you have one context-sensitive grammar, and then we go up the way to universal grammars and Turing machines and whatnot. So the further up you go, the less popular things are, and you don't want to write this with a context-sensitive grammar. So what we're working on is to extend such context-free grammars with constraints that tell you that one particular item is the result of this particular operation being applied on this other item. And these operations is something that we imagine can actually be extracted from code, because you can find out that the length that is being encoded in here actually comes from code and is being checked at this point. So we can extract these operations and feed them in and make constraints out of them. And this is how you can then represent constraints regarding with respect to checksums and length and of all of these other container formats and binary formats. Actually, Actually, I have a very nice master thesis on that, where I'm awaiting results soon, which is specifically geared towards checksums in input. The second thing is that what we need here, what we have here is actually multiple layers of languages stacked upon each other, like in media formats. You have, or say like the ISO OC networking model. Not sure whether this is still in textbooks, but say you have a layer where you describe things in terms of bits being processed. You have a layer where you think about these as data packets, and then somewhere up there you have the application layer. Same thing happens with media containers. You have a representation where you have individual bits with checksums and lengths, and then you have another representation where you actually talk about the context of all these individual frames that are packaged in here. And our goal is to bring these together, not only by having multiple grammars, so you can have one grammar for each layer that describes it, but there's the concept of so-called conjunctive grammars, which is a mostly theoretical result from language theory, but the idea is that you can take multiple constraints. So the idea is that you not only have disjunctions that tell you this can be I or B, but you can also have conjunctions. You can tell this can be A or B, and it also has to fulfill this other constraint. And the idea is that you can then express that a file has to fulfill the constraints that happen at the bit level, but also at the application level, and all of these together. You can also have negations in there, actually. Then you get Boolean grammar. Then you can say an input has to fulfill this, and must not be this. Okay, and then you can actually combine things like this is a kind of input that you'd like to avoid. So you have an explicit blacklist, for instance. So this is something that we have where we think of in the near future. We'll be able to infer these. The problem is production, because right now, if you only have disjunctions, production is a very simple thing. But as soon as you have conjunctions, you actually have to go into string constraint solving and others, where you, in the end, have to invoke something like Humpy or Z3 in order to fulfill those constraints. But again, this is classical. This is classical constraint solving. We have tools for that. We know how to do that. So it's not out of the reach. So two answers, two longer answers to a short question. Yes?
For many of the examples that you've shown wouldn't have been the proper way of doing that in the first place, writing any grammar to begin with.
Sorry?
So wouldn't have been the proper way to deal with these things to write a grammar in the first place, rather than, kind of constructing that as you go?
Well, even for a simple thing as a URL, writing a grammar can be difficult. Because if you write the grammar, you start to reason about what kind of characters can be in the path. What is the range of a port? Can I omit the port? What kind of characters are allowed in a password? Okay, this is the things that make you think hard. Okay, and it's important, but it's important to capture these constraints precisely, because these are precisely the things you want to test. Okay, and by having an automatic learner, or in this case an active learner, that infers those things for you by running tens of thousands of experiments, you get way more information than what you could ever do through manual testing and probing. So even for a symbol, even for something where we think we know how something is composed, formalizing this is actually manual work. And if you think about a format that you do not know, okay, and say you have some proprietary data format. I remember I was working. This was during my student time. I was working with some sort of vector drawing program, which had a proprietary file format in which everything was stored. So I had no idea what this looked like. So I loaded this file into my text editor, and the first characters in that file were, "So you're trying to find out the innards of a such and such file, eh?" Question mark. It was an insult. I mean, it's like abandon all hope, you enter here, or something like that. Okay, so it's definitely and now you think about so somewhere there's a hard disk in which somebody has stored millions and millions of pictures made with that particular program on a hard disk, and you have no idea what it is made of. But if we can extract the grammar, then we can then if we can extract the grammar for it, then we'll be able to identify what it's made of. And actually, if you think of it, we can create a universal XML converter. Take anything and convert it to XML using this very structure in the grammar to produce XML out of it. And whoops, all of a sudden you can reuse everything. So yes, there's plenty of usages for that.
I'm also thinking if people might want to replace their current implementation with a grammar-based implementation that they get off of your tool.
Well, if you have a grammar, then it's easier to create a parser again out of it. It's obviously easy to also if you think of it as an oracle, for instance, you can use the grammar to check whether outputs are valid, for instance. It's amazing that we love. Computer scientists love grammars. We do. If you do 1 year of studying computer science, you learn a bit about grammars and formal languages. Okay, and you need them later too. But bringing these things together. Here's my program, and here's the language. Okay, so far we've only seen this from the prospect of creating a specification and then implementing it, and creating a parser automatically from a written specification. Yes, we know that. This is a parser generator. But the other way around, this is some other way around. Here's a program. What's its input? That's a problem that has never been addressed before. And I'm not even sure whether the problem has been posed before. And I think the problem has not been posed before because so far, even though the answer is relatively simple, it simply was not obvious how to do that. Thing is, if you apply standard static symbolic techniques and have a parser, if you have a parser and you want to find out what it does using standard static symbolic techniques, you ever looked at a generated parser with its tables and everything? It's impossible to understand what it does. And also for a constraint solver, it's impossible because if you have a table with 10,000 entries, you're going to end up with a constraint that has 10,000 entries too. And the solution is, lo and behold, a grammar. So there was no such thing. And only by using a dynamic technique, I think, by looking at what's actually happening during the execution and combining this with active learning and testing, this is how we can now we have a good grip on how to tackle that problem. It's still going to be a decade of research till it all works out, and there's plenty of opportunities. So I encourage you all to. I'm happy to encourage you all to try these things out for yourself.
Okay, so let's thank Andreas one more time.
Pleasure.